Hello. In this lecture, we will look at CPU scheduling algorithms. We had seen in operating systems that a scheduler present would choose a particular process from the ready queue, and that process is assigned to run in the processor. Now, the question that we were going to analyze now is how should this scheduler choose the next process. Essentially, how should the scheduler choose a process to run on the CPU from the existing queue of ready processes. Now, to analyze this, we first look at execution phases of a process. Now, any program has been known to have two phases of execution. One is when it is actually executing instructions, which is known as a CPU burst, while the other is when it is blocked on an I/O or not doing any operations. So, in this particular case the CPU is idle. Thus, as we look with over time, a particular process would have some amount of CPU burst in which it would execute instructions on the processor, then it would have some idle time in which it is waiting for an I/O operation, then there would be a burst of CPU time and so on. Thus, there is always this interleaving between CPU bursts and idle time, that is waiting for an operation. So, based on this phases of execution, one can classify processes into two types. One is the I/O bound processes, while the other is the CPU bound process. Why do you make this distinction between I/O bound and CPU bound processes? Essentially, this is from a scheduling perspective. We would like to give I/O bound processes a higher priority with which they are allocated the CPU. Essentially, we want that I/O bound processes wait lesser time for the CPU compared to CPU bound processes. So, why is this required? We can take with an example. So, suppose we are using a word processor such as a Notepad or VIM, and we are giving this I/O bound process a very low priority. Now, suppose a user presses a key, because it has a low priority, it does not get the CPU to very often, and therefore, it would take some time before that key pressed by the user appears onto the screen. So, this may be quite uncomfortable for the user. Therefore, we would like to give the I/O bound process such as the word processor higher priority with which it will get the CPU, so that the user interaction with the CPU becomes more comfortable. On the other hand, if we look at CPU bound processes, we could give it a lower priority. Now, for instance, if you take one of these applications, the CPU bound applications, like for instance let us say GCC, that is compiling a program, and let us say you are compiling a large program which takes 5 minutes. Now, it will not affect this user much if the time taken to compile that particular program increases from 5 minutes to say 5.5 minutes. Thus, CPU bound processes could work with a lower priority. This classification between I/O bound and CPU bound is not a rigid classification. That is, a process could be an I/O bound process at one time, and after some time it could behave like a CPU bound process. So, to take an example of a process which behaves both like an I/O bound as well as CPU bound, you could take for instance Microsoft Excel. When we are actually entering data into the various cells in Excel, it acts as I/O bound process. So, it behaves like an I/O bound process with small CPU bursts and large times of I/O cycles, while on the other hand, when you are actually computing some statistic on the data entered, Excel will behave like a CPU bound process, where there is a large portion of CPU activity or the time taken to actually operate on that particular data. Now, let us come back to the question about how the CPU scheduler should choose from the queue of ready processes the next process to execute in the CPU. There could be several ways in which the scheduler could make this choice. Essentially, there could be several CPU scheduling algorithms which would look into the queue and make a particular decision. So, in order to compare these various scheduling algorithms, operating systems textbooks or operating systems research defines several scheduling criteria. So, these criteria could be used to actually compare various scheduling algorithms to see the advantages and disadvantages of each of them. So, let us go through each of these scheduling criteria one by one. The first scheduling criteria is the CPU utilization. The scheduling algorithm should be designed in such a way so as to maximize CPU utilization. In other words, the CPU should be idle as minimum time as possible. The next criteria we will look at is the throughput. Essentially, scheduling algorithms would try to complete as many processes as possible per unit time. A third criteria is the turnaround time, and this criteria is looked at from a single process perspective. So, turnaround time is defined as the time taken for a single process from start to completion. The fourth criteria is response time. So, this is defined as the time taken from the point that when the process enters into the ready queue to the point when the process goes into the running state. That is, the time taken from the instant the process enters the ready queue to the time the CPU begins to execute instructions corresponding to that process. Another criteria is the waiting time. Now, this criteria is based on the time taken by a process in the ready queue. Now, as we know, processes ready to run are present in the ready queue, and it is required that they do not wait too long in the ready queue. So, scheduling algorithms could be designed in such a way that the waiting time or the average waiting time in the ready queue is minimized. The final criteria we will see now is fairness. The scheduler should ensure that each process is given a fair share of the CPU based on some particular policy. So, it should not be the case that some process, for instance, takes say 90% of the CPU, while all other processes just get around 10% of the CPU. So, all these criteria need to be considered while designing a scheduling algorithm for an operating system. A single scheduling algorithm will not efficiently be able to cater to all these criteria simultaneously. So, therefore, scheduling algorithms are therefore designed to meet a subset of these criteria. For instance, if you consider a real time operating system, the scheduling algorithm for that system would, for instance, be designed to have minimum response time. Other factors such as CPU utilization and throughput may be of secondary importance. On the other hand, a desktop operating system like Linux will be designed for fairness, so that all applications running in the CPU or in the system are given a fair share of the CPU. Criteria such as response time,